Alright guys, so now we're going to start going over the calculations for determining the sun vector, the most important part of this lab. So we're going to start out by going over the main governing equations for turning our zenith angles that we calculated in the last section into the sun vector. Now the sun vector is basically a vector with an x, y, and z component that points from the origin to where the sun is supposed to be. The equation turns out that it's going to be the tangent of the x or y component over the square root of each component squared. For instance, for x, we're going to have the tangent of our zenith angle in the x direction divided by the square root of the tangent of zenith angle in the x direction squared plus the tangent of the zenith angle in the y direction squared plus 1 squared. Now we're using 1 because we want this to be a unit vector of length 1. This equation is going to be very similar for sun vector x and sun vector y. For sun vector z, it's a little bit different. We're just substituting 1 in on the numerator instead of having the tangent of the zenith angle. Now once we have the x, y, and z component of the sun vector, we're going to convert these to spherical coordinates, which will give us an azimuth angle, an elevation angle, and an r value. And r is basically just the length of the vector, which we already know is 1. So that's just going to be 1 every single time we output it. And we're also going to display the azimuth, elevation, and r in our command window so that we can see it every time a new value is calculated. So earlier on in the code, we plotted the hemisphere in a new figure. And now we want to be able to plot where the new position of the sun is on that hemisphere. But we don't want these plots to add up over time. So every single time we plot a new dot on that hemisphere and do more calculations and we come up with a new coordinate for a new dot, we want to be able to get rid of the old one automatically. So what this is saying is if h3 is not equal to 1, h3 is a variable that we defined up here. We initialize in the calculation section. It starts out as 1, and then as soon as something is plotted, it's assigned to a variable right here. So as soon as we plot that point using the scatter3 function, that's assigned to the variable h3, and h3 is no longer 1. So anytime h3 is not 1, it sets h3 to off. Its visibility is off. That means we no longer can see it. So the first time this code runs, h3 is in fact 1, so it skips this if statement. Now, like I said, every single time a new point is plotted, it's going to do some calculations with the sun vector and plot that point on the hemisphere. So the first thing to do is to convert the elevation angle that we calculated up here after converting it to spherical coordinates. We're going to convert that to degrees. So now it's in degrees. Now we want to plot this point, but the thing about MATLAB is that plotting actually takes a little bit of time. And so we don't want to plot this point every single time we receive a new data chunk from the Arduino. So right here, I'm saying every single time we receive a new line of data from the Arduino, the count variable is going to go up by 1. Now we started with count is equal to 0, and every single time this loop runs, it adds 1. So I'm saying every 4 times we receive a new piece of data from the Arduino, we're going to plot a new position. Now you can change this number to be whatever number you want. The higher the number is, the more infrequently you're going to receive a new plot on your figure. But also the higher, if you decrease this number, the higher chances of you crashing your code, those chances will increase. So 4 or 5 is around a good number. Once we plot this point, we realize that we built this configuration to have a very specific field of view. If we do a calculation and the plotted point is outside our predicted field of view, we want to be able to tell if that point is valid or not valid. So we have 2 if statements here. One is saying if the elevation angle that we calculated is past our field of view, or within our field of view, then we're going to plot that point with a blue dot, signaling that it is probably a correct calculation. Now, if we do a calculation and we get an elevation angle that is beyond our field of view, making it impossible for the sensor to actually be detecting anything outside our field of view, we're going to plot the point regardless, but we're going to plot it in red, signaling that that may or may not be accurate. Now, once we plotted our hemisphere, we also want to be able to tell which way is north, east, west, or south. So remember that our hemisphere is actually in the reference frame of our sun sensor configuration. So we are just plotting the number or the letter N, E, W, or S on a two-dimensional plane, on the XY plane, underneath the hemisphere. And that's just for us to be able to say which way the sun is actually compared to the origin of our sun sensor configuration. And so you use the text function in order to just put this letter in this specific position. So x is equal to 0, y is equal to 1.5. It has the color of red and has a very specific font size. And we'll do that for each letter. View is a function that lets you change which view you're actually looking at the hemisphere. If you have it view as 0, 45, that means you're looking from the south and looking north. So that's probably the best way to do it, but you can play around with that if you want. We also added a very short pause in here after every single time something is plotted, so that just gives MATLAB enough time to catch up and continue with the calculations after the new plot has been plotted on our figure. And then at the end of that if statement, we're going to add 1 to our count, like I said before. I think that brings it to a close, so let's start running this program and see what we get. So there's our hemisphere. We're pausing for 3 seconds. And there you can see that blue dot is moving around the hemisphere. And north, east, south, and west letters tells us which direction is which in the reference frame of our sun sensor. You can see a few dots turn red there. And again, that means that those points were likely outside of the anticipated field of view of our sun sensor. So they may or may not be accurate.